In our previous lesson, we have tackled the area under the curve, which is the area enclosed between a curve and the x-axis. However, in this lesson, we're going to be going through how we could determine the area between two curves. So instead of just working with an area enclosed between a curve and the x-axis, what we would do here is determine the area that is enclosed between two given curves. However, when you were determining the area under a curve, it was really important to study the relative position of the curve with respect to the x-axis in order to know where the curve is positive or negative. However, when you're working with the area between two curves, as you can see, the relative position of the curves with respect to the x-axis is actually irrelevant here. It doesn't really matter how the curves are located with respect to the x-axis. What matters is the relative position of the two curves with respect to each other. So which one is in fact above the other one? So the area under a curve, between two curves is in fact the integral of the difference of the two functions. For example, if we were to just look here at a quick example to illustrate why is it that we really consider the difference of the two functions in the integral in order to determine the area between two curves. So if I have here y equals to f of x, and I have here y equals to g of x. Now the area under the two curves is in fact defined by this region, of course, over here between A and B. So this is the area between the two curves. As you can see, the blue region is defined by the area under the curve of f of x minus the area under the curve of g of x. So the blue region, its area is in fact the area of the black region minus the area of the red region, and that is why whenever we need to find the area between two curves, what we would do is in fact integrate the difference of the equations of the two functions, because the integral of f of x gives me the area under the curve of f, and the integral of g of x would give me the area under the curve of g of x. So subtracting these two integrals would in fact give me the area between the two curves. However, we do not always have f of x above g of x. So we could have fx greater than g of x over the interval ab, we could have fx smaller than g of x over the interval ab, or we could have the two functions changing their relative position over the interval ab. So for that reason, the integral from a to b of the absolute value of f of x minus g of x does in fact give me the area between the two curves. So if f of x is above g of x, so if the curve of f is above the curve of g over the interval, what you would do is integrate f minus g. If the curve of g is above the curve of f, in that case what you would do is integrate g minus f, as we will in fact see in this quick example. So in this example, we have f of x to be equals to square root of x, and we have g of x to be equals to x over the interval 0, 2. So we already have the graphs here. The red graph is the graph of y equals to f of x. That's the curve representing y equals to square root of x, while the blue line is in fact the line corresponding to the equation y equals to x. So over here, over the interval 0, 2, the area that is enclosed between the two curves is defined by this following area. So since the interval ends at 2, then we do end the region between the two curves at x equals to 2. So this is the area that is enclosed between the two curves. So you can see here that between 0 and 1, we have the curve of f to be above the curve of g, while between 1 and 2, we have the curve of g to be above the curve of f. So for that reason, since the area between two curves in fact consists of integrating the absolute value of f of x minus g of x, then over here between 0 and 1, what we would do is integrate f minus g, because the curve of f is above the curve of g, and between 1 and 2, what we would do is integrate g minus f, because the curve of g is above the curve of f. So here the area between 0 and 1 of f of x minus g of x dx, and then plus the integral from 1 to 2 of g of x minus f of x, because over the interval 1, 2, the curve of g is above the curve of f. Now you'd notice that that is the same as minus the integral from 1 to 2 of f of x minus g of x, if we were to follow the exact definition of the absolute value. So the absolute value of f of x minus g of x is f of x minus g of x, where f is above g, and it's negative into f minus g, where f is below g, which you'd notice that these two are in fact equivalent. So integrating here, replacing and integrating, so that's the integral from 0 to 1 of square root of x minus x dx, and plus the integral from 1 to 2 of x minus square root of x dx. So integrating an antiderivative of square root of x, as we've discussed when we set up the table of antiderivatives in our introductory lesson on antiderivatives, that is in fact 2/3 x square root of x. That's the antiderivative of square root of x. So minus half x squared for the first one, that is between 0 and 1, plus, now over here you notice it's the same terms, it's just their opposites. So I do consider the opposite of the antiderivative as half x squared minus 2/3 x square root of x between 1 and 2. So over here, just replacing upper bound minus lower bound, I would have for the upper bound 2/3 minus half, and then for the lower bound it's in fact a 0 for both, plus, now for the upper bound here I have a 4/2, which is a 2, then for x equals to 2, this is 2 square root 2 times 2/3, that's a 4/3 square root of 2, that's for the upper bound of the second one, minus for x equals to 1, it's again half minus 2/3. Simplifying that would give me a equals to 7/3 plus 4/3 square root of 2 unit squared, which is approximately 4.22 unit squared. So that is regarding the area between these two curves between 0 and 2.